Anyone recording?
Yeah, I think I can start the recording. Oh, there you go. Sarah's done it. Perfect.
Okay, brilliant. Okay, over to you, Billy and Mike. Thanks a lot.
Okay. Well, hello and welcome to our presentation about Millstream Bridge refurbishment, which is a project we did recently here at Tony G. I'm Mike Armistead. I've been working at Tony G for about a year now.
Hi, my name is Billy Pullam. I'm a design engineer at Tony G and Partners in the Manchester office. I've been at Tony G for 4.5 years, where I started as an engineering apprentice. So throughout the presentation, we're going to cover a bit of background to the scheme, the proposed works, some constraints we came across during the project, FFU bearers and side-cut sleepers, the sustainability aspects of the project, the horizontal and vertical track design, the guardrail and adjustment switches, and the staging of the project.
So yeah, we'll talk firstly about the background of the scheme and firstly about its location. It was located in the southeast of England on Millstream River Bridge. This is an underbridge located at the London end of Ashurst Station in Kent, near to a town called Tunbridge Wells. The bridge itself was located at 32 miles 44 yards on the SCU1 ELR, which carries the up and down non-electrified lines over Millstream Bridge. So we have AIVR footage here of the bridge itself. I think we can see the line speed as 70 miles per hour, but we'll start off by taking you through the footage itself. So for those who don't know, AIVR essentially allows you to see it from the POV of a train, basically point of view, and it's on most ELRs in the country, which is great. We use it here for seeing the existing conditions of a project, spotting and identifying obstructions, and it's ideal for gauging sort of a good addition to viewing a topographical survey, basically. So you can see here we're starting at Ashurst Station, setting off, so instantly you can see how close we are to Ashurst Station itself, and coming straight up to LRPs here on the timber sleepers up to the bridge, and you can just see the guardrail which runs on top of the longitudinal timbers which span the length of the bridge. You can also see metal grating along here, which we eventually replaced as part of the scheme. And that should be the footage going across the bridge there. So you can use that for various different lines across the country.
So a bit on the existing site. Millstream Bridge is a 5-span underbridge consisting of 4 wrought iron longitudinal riveted plate girders per span, with horizontal and cross bracing and outer parapet beams along both sides. The tracks lay on longitudinal timbers, which are in turn supported on traverse timbers supported on the main girders. The deck is of open construction with metal grating. The substructure consists of brickwork abutments and 4 piers of wrought iron columns with cast iron crossheads. The structure has a skew of approximately 50 degrees. The bridge was built in approximately 1885, and in 2013 it was assessed and strengthened and found to generally be in fair condition. Main defects included the deterioration of metalwork protective coatings, leading to surface corrosion on components and fractures in the abutment brickwork and padstones, which were assessed as non-critical. Various levels of decay were recorded in the existing timber sleepers and bearers across the bridge, and it was recommended that they be replaced with non-timber materials. So a bit on the proposed works.
Yeah, so it's a renewal scheme, and the initial plan was supposed to be a simple track on-off scheme with the removal and replacement of the long timbers which span the length of the bridge. But upon further inspection, we found that the traverse timbers underneath the long timbers were decaying and had expired, which meant they had to be either removed or replaced as well. So you can see the design in the top right with the longitudinal timbers in blue and the traverse timbers in green. The initial plan was to replace both of these and attach them to the steel structure of the bridge. But the final decision we came to was replace both of these elements with FFU bearers, which could be bolted to the bridge itself. And that was the decision we came to in the end.
So the proposed works to realign the existing track system, reusing the running and guardrails. A new synthetic sleeper track support system would be installed across the bridge. Relocation of existing bridge intermediate braces that were clashing with the synthetic sleepers. Providing new secondary steelwork to support the bridge walkway infill grating. Replacing the existing infill grating across the walkway. All exposed bridge metalwork was prepared and painted. A schedule of repairs was proposed, and minor repairs on the bridge structure and abutments were carried out. New precast concrete end slabs were installed at the abutments. So a bit on the constraints. We're going to go into more detail on these throughout the presentation, but the constraints that we came across, there was an existing cant transition over the bridge. There was a vertical hump over the bridge. Ashurst Station was in very close proximity at the high mileage end of the structure. There was guardrails and adjustment switches, and there was a constraint of the possession timings. So the FFU bearers. These are the FFU bearers which were installed over the structure. And like Mike said, the depth of them accounted for both the longitudinal timber and the cross bearer, which were there previously. The FFU bearers could be specifically designed to the millimetre to install the track vertical alignment. There were 14 different types of bearer designed by the civils team, and then various depths of packers were then used to get the track up to its desired level and install the cant alignment. So on the screen there, that's the bearer schedule which the civils team put together.
And there is some benefits to FFUs. Firstly, what it stands for fibre reinforced foamed urethane. And the way to make these is essentially have glass fibre strands which are soaked in rigid polyurethane resin and then can be cured at a high temperature to create what is essentially a man-made timber with all the properties of timber, but with slightly more chemical resistance. What's great about them as well is they're 100% recycled, which is ideal for strategies we know Network Rail has about the improvement in sustainability. They also have a service life of around 50 years, but there is some FFUs in place at the moment which look like they're about to outlast that, so which is another positive for the FFUs as well. And ideal for this scheme and implementing the vertical alignment of the track, they can be custom manufactured to the millimetre, which is why we used it for Millstream. There was a disadvantage though we got with the FFUs, which was the fact that they were custom made meant they had to be pre-ordered and shipped over from Japan. So luckily we knew this ahead of time. We were able to plan ahead and it did not affect the final date of the project's completion.
So the next bit is on the side-cut sleepers and the sustainability aspects of the project. So the detail on this slide shows the concrete slab, which was installed at both ends of the bridge to mitigate the structure skew. It enabled the FFU bearers to continue to the end of the structure, regardless of the 50-degree skew. After the FFU bearers finish at the end of the slab, existing timbers were replaced with side-cut sleepers. And due to the new guardrail that was installed off the bridge, new sleepers were required to fix the guardrail too.
So then what are the side-cut sleepers? They're composite sleepers manufactured from a unique blend of recycled plastics and very similar to FFUs, they're reinforced with glass fibre. Another benefit of them is they perform very well in various conditions. We know there's some in place in America right now and some in the UK, and there's varying temperatures that they can be exposed to, and they're performing very well in that case. They can also accommodate numerous transport, e.g. Trams and subway, but also what could be very important for the future is heavy freight as well for transporting heavy loads. So that's also a plus for the side-cut sleepers. And some of its FFUs, they can be fitted with a wide range of custom base plates and clipping systems for various designs you might have.
So one of the reasons for the use of side-cut sleepers was due to the ban of creosote. Creosote is a treatment for timber sleepers, which is used to prevent rot. After it was classified as a Category CB carcinogen by the European Chemicals Agency and a persistent bioaccumulate and toxic substance, there was a European ban of creosote. So Network Rail's response to the European ban was to cease procuring softwood sleepers from July 2021.
Yeah, so a bit more on some of the strategies Network Rail have. There is currently one in place that promotes the increase in recycled materials on the network, and to also recycle the current materials that are in place at the moment. Like I said, this target is what is 2050. So currently sleepers are the second highest embodied carbon material in track, second to only the rail itself, due to the fact that steel has very high embodied carbon. But the reason why cycles are quite good is because the fact that they would replace the hardwood, which is used across the network at the moment, which is sourced mainly from Brazil, which is a huge factor in deforestation itself. And also it would replace either steel or concrete sleepers, which we can show you on the next slide, are also very high in embodied carbon. So the graph here will show the tons of carbon dioxide equivalent per track kilometre of embodied carbon dioxide equivalent. So you can see steel there's the highest by quite a long way. And you see side cuts on the far right, which is a great reduction from what is closest to it, G44 concrete with undersleeper pads, approximately 3 times lower than that. And say if we were assuming a 25 year lifespan, we could see a reduction in the embedded carbon of between 120,000 and 400,000 kilograms carbon dioxide equivalent. The reason that's quite a broad number is that side-cut sleepers haven't been in place 25 years yet, so it is an estimate, but that's still a great reduction. A bit of a breakdown per sleeper, which is probably easier to understand. You can see if we go to concrete at the top, 309 kilograms, plus the 4 kilograms of steel fixing and 4 kilograms rubber, you get 125 kilograms CO2 per sleeper. And then untreated hardwood, slightly more, steel much higher. But then you look at side cut with 74 kilograms plus 26 kilograms, sorry, of steel base plates and fixing. That's only 36 kilograms of carbon dioxide per sleeper.
So a bit now on the horizontal and vertical design for Millstream. The existing track over the bridge is a horizontal transition where the cant changes from 0 mil on the low mileage end to 50 mil on the high mileage end. Ideally, the proposed track would have a constant cant and radius over the bridge. This design option was explored, but it resulted in large sloughs over the structure. Like for like alignment with minimal sloughs was required due to the fact the design was installed in 4 stages and therefore needed to tie in the centre of the bridge. An overview of the full horizontal alignment shows it tying in at the low mileage end to a straight on the down and a curve with radius 17,000 metres on the up, both with 0 mil of cant. There's then the horizontal transition over the structure with the cant increasing to 50 mil. The up then ties in with a radius of 1,600 metres and the down ties in further down into the platform with a radius of 2,200 metres. So when we started the design for the vertical design for Millstream, we explored a couple of design options. One design option is the one on the screen, the one to have a vertical curve over the bridge. This option kept the lifts to a minimum over the structure, however, wasn't the preferred option as it resulted in more elements of shorter lengths. And this wasn't ideal when the line speed is 70 miles an hour and none of the elements achieve 2 seconds. The other option, which was the chosen design, was to have a single grade over the bridge. This did, however, result in a large amount of lift on the low mileage end to the structure. We've been instructed that we could not lower the track over the structure. We needed to tie the vertical alignment in as soon as possible after the structure, due to Ashurst Station being in such close proximity, and also due to the track being installed in 4 stages, it had to tie in at the centre of the bridge. The design of the vertical alignment was very constrained. Yeah, so that's just a closer view. You could see the high amount of lift we had on the low mileage end there, and it created a pinch point at the high mileage end where there was basically no lift at all. So as I said, the Ashurst Station was right next to the end of the structure. The client had said they didn't want any track work through the platforms, but due to Ashurst Station beginning within 5 meters of the high mileage end of the structure, it was inevitable that some lift and slews would have to take place through the platforms. Fortunately, due to the poor platform X and Ys throughout the station, the lift and slews which had been designed actually improved the platform gauging.
Yeah, as we did talk about earlier, another constraint was the guardrail and the adjustment switch. What I did miss earlier was the fact that the current guardrail in place was a non-compliant. So the existing bridge has no robust curbs, and which meant that any guardrail had to extend 18 meters beyond the structure itself. So when we were taking this into account and designing it, we found that it clashed with one of the adjustment switches on the Ashurst Station side. And then this had to be overcome. The client preference was to just remove the adjustment switch altogether, which would essentially mean the track would have to be stressed across the structure itself. And then it was thought that this could possibly fail a track structure interface analysis. So in the end, the final decision was to come up with a bespoke unit design, which we'll show on the next slide. Here it is from one of our drawings. You can see in the blue circle there, the adjustment switch and the guardrail attached to the same FFU bearer. The direction of travel right to left there with the gathering panel coming up to the guardrail itself. Here's a real life photo overhead. You might just be able to see the adjustment switch in here next to the orange cables and the gathering panel. See, it's within Ashurst Station itself.
I think the final constraint that we mentioned was the limitations with the possession timings. This meant that the installation had to be split down into 4 stages. And like I've said, that required the horizontal and vertical alignments to tie in the centre of the bridge. So there was 1 week between stage 1 and 2, 5 weeks between stage 2 and 3, and approximately 10 weeks between stage 3 and 4. And you can see I've labelled on there which ends were in which order. So the fact the installation was staged created a hazard due to the interface between the old and new guardrail. There was exposed guardrail ends in the direction of travel, and the arrow there highlights the direction of travel. It meant that if a train was to derail, there was a gap between the old and new guardrails, which mean the train could derail off the bridge. But this risk was minimised by ordering the staging so that the risk was only there for 1 week between stages 1 and 2, as opposed to the larger gaps between the other stages. And a temporary speed restriction was also applied while this hazard was there. So the finished construction.
Yeah, we have the before and after shots. The one on the left, Millstream, before any works were prior to being completed, and the one on the right with our new yellow grating just before construction was finished. These were on-site photos, and then we have a photo taken from the overbridge within the station. You can see that's the fully finished bridge there with the new guardrails that within compliance that go 18 meters beyond the structure, and yeah, the new yellow grating we put over the top. You can't see much of the works underneath it. You can just about see the FFUs though as you go through the bridge here.
So we're now currently working on a project called River Medway Underbridge, where we're replicating the same design principles. It's currently a long timber bridge, and we're going to replace that with FFU Bearers, just as we did with Millstream. And the guardrail also needs extending 18 meters off the bridge, and it's going to be a similar situation with the adjustment switches as well.
Yeah, thank you very much.
Thank you.
Thanks for listening. Have you got any questions? Yeah.
But thanks, Mike. Very excellent presentation. I think there's a couple of questions in the chat. I'm going to squeeze a question in for myself, if you don't mind. The FFU section. So you've combined the longitudinal timber and then the crossbeam timber together. So you've replaced it with using these FFUs. How bespoke were they in different locations, or did you standardise it?
So there was 14 different FFU bearers which were designed and used across the bridge, and then there was packing used to bring it up to the desired level and apply the cant.
Okay, thank you. And is this a common solution now, or has this been used? Is this kind of replacing the crossbeam and the longitudinal together? Is this a common solution now across the network rail, or is this a new one?
Not sure about other companies, but I think this was the first one that we'd done. But like I said, we're already replicating that same design principle on another project.
Okay, I've got a couple of questions in the chat. I don't know if you've seen them. Please forgive me if I get the pronunciation wrong here. Shoaib, you've got RFFU's cost benefit. How is it maintained over the lifespan? Have you got any details on that?
I can't explain the cost benefit over the lifespan or how it's maintained. I'd be able to find that stuff out for you though, if you'd like to hear more about it for sure. It's not something we came prepared with, but definitely can find it out.
Is there general feedback that it's minimum kind of, you're not going to get the deterioration that you get with softwood bearers? Is that correct?
Yeah, it's got a greater chemical resistance, which is ideal for any sort of external structure which is exposed to the elements. But yeah, even with the ban on creosote, it's still got better chemical resistance than those softwood timbers. Okay,
thank you. And then the next question again was, were there any grade-to-grade elements connected less than 2 millimeters, or was a vertical curve provided between the grade-to-grade, or all vertical curve achieved above the minimum length of 20 meters? So you were showing a cross-section before of your vertical design. Was that?
Yeah, so we had vertical curves in between all the elements of above 20 meters. I think on one line we did have to have a reverse vertical curve back to back in order to be able to tie in to Ashurst Station as soon as possible after the structure.
Okay. Is there any more questions from people on the call? You can just put your hands up if you have got any questions. Oh, I've got one in the room. Harvey Tatlow's got a query, so go on, Harvey.
Hi guys, a really good presentation, thank you. Just a quick question. Obviously, you replaced the guardrails there. I was just wondering about sort of, as they call them, the butterfly rail at either end, noting that obviously at the station end, there probably wouldn't be any room to get something in there. But on the, would it be the low mileage end, the opposite line? How come you didn't put any gathering rails in?
It was considered, but like you said with the platform bit, it was the same on the other end. There just wasn't enough space for that.
Thank you.
Okay, any other questions from people on the call? I've got one for myself, but there we are. Yeah, so the next bridge you're doing at the moment, Mike, Billy, how's that going? Have you got similar constraints there?
Yeah, so we've got the same constraints with the adjustment switches. Fortunately, we don't have the constraint of a platform, but there is another long timber bridge in close proximity as well, which we are aiming to tie in the design before. Yeah, and the vertical alignment is a bit better on this one, so we've not had as many problems with that. It's good to, as we've already done it before, that's helped loads with being able to produce the design.
Hi, Billy. I'm Shoaib. How are you doing?
Hiya.
Good, mate.
Right.
How are you?
Hiya. It was just my questions that were put onto the chat, into the meeting chat. I just wanted to ask one question. Because you were closely to the platform, did you have to tie in with the existing radius, or was it an existing straight? Did you have to keep the same existing radius, or did you have to re-put a brand new radius because you're so close to the platform? Did you have to connect with the previous alignment?
I think the radius may have changed slightly to what was there already, but then we undertook all the platform gauging and everything in clear route, and it actually improved what was there today.
Brilliant. Thanks, Billy.
Okay, anyone from anyone else question wise? If not, I'd just like to say, Mike, Billy, thanks again for presenting. I know you did a very shorter one the other day, but it was like a young engineer's presentation. I think I'm allowed to say you're definitely younger than me, so fair play for presenting. Really professional, and it's great that you've taken the time to go a bit further into the works you've done here. And if you've got more schemes to go in the future, please come back to us and show us what you're doing, because it's good to understand what's going on. I don't know how we do the virtual applause now, but you can do virtual applause on Teams or physical applause. But yeah, thanks again. I'll do a round of applause in the room. So thank you very much.